Okay, now we just looked at permanent magnets, the kind of magnet that you're most used to looking at. We'll look at one more after this, which will be the magnetic field from a current. That's sort of how you're going to have an electromagnet, right? So you know how to generate currents with batteries and resistors and wires and things like that. And then you can make an electromagnet, which we'll talk about next time. But this time what we're going to talk about is what happens to all the other materials, right? And everything is magnetic. And you'll notice that, for example, I put up a levitating frog video on eCampus. That is a non-magnetic frog, or not non-magnetic because it somehow interacts with the magnetic field, but it is not a permanent magnet. There are no current loops around it. The frog isn't wearing a belt with a battery on it or anything like that. The frog is just levitating in the field. So how does that work? Right? So that's what we want to talk about now. And basically, all objects, when placed in a magnetic field, magnetize here I am. I want to make that more complicated, but that's all you really need to know there. I mean, there are two kinds of these things, and I'll talk about that in just a moment, but in general, everything magnetizes, so that magnetic moment is going to be equal to this thing called the magnetic susceptibility. That's going to be over mu naught. Mu naught is the permeability of free space. So we met the permittivity of free space previously. This is the permeability. Of free space. Mu naught is equal to 4 times pi times 10 to the minus 7. I believe Tesla per amp per meter. I think that's the right way. Tesla is what the magnetic field is in, and this was the susceptibility. This is the magnetic susceptibility. It's different than the what was that thing we talked about? The electric susceptibility. And this is the magnetic field. We'll talk a lot more about that later. The next lecture will be how each one of these things that we talk about, or 3 things that we're going to talk about, which is a moving particle, a magnetic moment, and a moving current, or a steady state current, reacts to a magnetic field. That will be next time. And after that, we'll talk about how each one of those generates. Each one of those generates a magnetic field. All right, and this is your volume. So it is similar to what we just talked about, right? We just talked a little bit about a permanent magnet, and in that case, you don't have this field dependence, right? Because it has an internal structure already. Most objects don't have that internal structure. They don't have those interactions between the different atoms that cause it to self-magnetize. So in this case, it's the external world that's causing everything to magnetize. Now there are 2 ways to do that. One is with a paramagnet. In that case, the uncompensated electrons paramagnetic material. Maybe like copper or something like that. I think copper would be one. I have to think. Align with the field. And what I mean by align is that that has a positive susceptibility. Okay, and let's see, how does that work? So let's start off with B equals 0 here. Let's go ahead and go on. Let's see. I'm not really sure which line I have to worry about. So if B equals 0, then you have these guys all canceling out. So we have 6 spins here. You have like 6 times 10 to the 24th spins or something like that in a real material. But each one of these atoms has, or each one of the electrons in the atoms that's uncompensated, there could be more than one. Each one of these aligns in a different direction at room temperature in no magnetic field. But when you put the magnetic field on, what happens is that one or two of these will just switch, they'll change, right? So if we have the B coming up this way, if we have the magnetic field going this way, these guys will try to align with it. So instead of having this setup where everything's every negative has a matching positive, right? So each one of these is actually negative and a positive matching. Over here, we don't have everything matching, right? So we've got these two compensate for each other. These two don't. So this guy has +2, and this guy has 0, right? So this guy's unmagnetized, this guy's magnetized. And what this means is that you get a positive susceptibility. So if we have here a magnetic field, and this is your dipole moment, you get a upward sloping line like this, and that slope is this number chi. Now you might think that if I spent all this time saying something goes up, then maybe something else goes down, and that's true. And we'll talk about that next. And in a diamagnet, there are no uncompensated electrons, or there are very few, just thermally, I guess. So the atoms in a paramagnet or diamagnet change their orbitals to oppose an applied field. And so that's a negative susceptibility. All right, so basically what happens there is, if B equals 0, none of the individual atoms inside of the material is magnetized at all. right? So B equals 0, nothing's going on. It's only when you apply that field, like that, that you get this reaction where it takes each one of the elementary magnets here, changes their orbitals so that each one of those elementary magnets ends up pointing down through the orbital interaction, basically because there's a current loop going through there, something like that, although it's more complicated. So it's different from this guy where you have a bunch of electrons that already have, just by the fact they exist, a magnetic moment. These atoms have no net magnetic moment themselves. It's only when you apply the field that that magnetic moment occurs, right? And you'll notice that all these arrows are pointing down. So when we do the same plot, M of B, we go down instead of going up. And this is now your susceptibility, and it's negative because it's pointing downwards. In both cases, you'll see everything's 0 there. And it's 0 when there's no field. It's only the field that's keeping these things magnetized. As soon as the field goes away, these things are no longer magnetized. Right? So that's more or less what happens with normal materials. You might think that this is not very important, but lots of different ways people levitate things is with diamagnets, right? With the diamagnetic moment. And we'll talk a little bit about that in the example. So we'll talk in this example about creating a magnetic moment in a frog, let's say, that maybe goes along with that video a little bit. And then in the next lecture, which will be about forces on these objects that we're talking about here, these magnetic moments, as well as some other things. In that, one of the examples will be to calculate how much force is, or how much field is required to levitate that frog. Okay, that spherical frog. It's going to be a very, very well-fed frog, so that volumes are easy to calculate. All right. So that's where we are now. Like I said, next time we'll talk about, or in the next part of this, we'll talk about how to get the magnetic moment of a current loop, which is a very important way to determine these things, or to talk about these things. All right?